everyone. My name is Grisel Diaz Ramirez, and I am a senior statistician at the Division of Geriatrics, University of California, San Francisco. And today I would like to share our work on mixed effects model and complex survey data with the GLIMMIX procedure. At my position at UCSF, I work very often with large-scale survey data in the development of a regression model for a better understanding of risk factors for health outcomes in older adults. Longitudinal data are widely used in the clinical and epidemiology fields. And in that matter, data from large-scale national representative survey samples are very useful in longitudinal studies for several reasons. One of them is that respondents are usually followed over extended periods of time. A broad range of health and demographic information can be collected, and a large number of respondents can be included. In the analysis of survey data using mixed effects model, one can have two main components. One component is the fixed effects part that describes how the population means differ across subject characteristics. And the second component is the random effects that capture the variability among subjects or other units. In a typical longitudinal survey data, you can have multiple observations per subject across wave, and also subjects are grouped into clusters and strata. The mixed effects model needs to account for the survey features probability weights, cluster, and strata. In this type of model, the random effects accounts for correlation of observations within the same subjects and correlation of subjects within the same cluster or strata. If we fail to account for this survey feature, we might get biased population estimates and wrong inferences about the population of a study. So it's very important when you're using, when you're fitting a mixed effects model with survey data to include this survey feature. However, this area is still an area of active research, and currently there is no survey analysis procedures in SAS for mixed model. Previous work has shown how to use the GLIMMIX procedure to fit a weighted mixed model while accounting for cluster. However, when you have many levels of strata and cluster, this can really be very computationally intensive and complicated to optimize. So in this paper, we show 5 methods of accounting for survey feature. We compare the estimates, the 95% confidence intervals, and running time among these methods. Our goal was to find a balance between obtaining accurate estimates with correct standard errors and manageable processing time. Finally, we make some recommendations on the specification of the final model. In this first slide here, I show you the right way of fitting a mixed effects model with survey feature. In this particular example, I'm fitting a mixed effect model with 2 splines, random intercepts and slope, and the survey feature probability weights and cluster. I highlight here the features that are more important in the survey feature design. The first one, we have a method equal a quadrature. This means that we are using the quadrature algorithm to get the weighted likelihood function. Then the empirical equal classical allow us to use the sandwich estimator to obtain the standard errors for inferences on the fixed effects. Then we have 2 random statements here. The first random statement, we are obtaining the random intercepts for the variable cluster bar. This variable is a survey design variable that is a combination of strata and cluster, and is accounting for the correlation of IDs within the same cluster. Then we have the second random statement that we are obtaining random intercepts and random slope for each ID, here represented by new ID, nested within cluster bar. And then we specify the probability weight corresponding to each of these respondents in the sample that we have. So this is the right way of fitting the mixed effects model while accounting for this survey feature that I just mentioned. However, this model can be very computationally intensive and hard to optimize, and this can take a long time to finish. So in the next slide, I will show you alternative ways of fitting this mixed effects model while accounting differently for different survey features. In the first slide here, I'm showing you what we call the reference method. In this case, we are not accounting for any survey feature. So you see here that I have crossed out the empirical classical option and also the probability weight. So basically here, this is the baseline model that we are comparing with for the rest of the method. And then the second model, we add leader by leader or step by step each of the survey features. So first, we are going to add the probability weight in the second random statement, as we saw in the first slide here. And then we keep this method equal a quadrature, so we are obtaining the weighted likelihood function. And then a new feature here is the fast QAP sub-option. So this option within the quadrature algorithm allow us to reduce the number of random effects that the model needs to fit. And in reducing the number of random effects, this also in turn reduces both the computational demand and memory usage. And consequently, we have shorter running time. So this is very nice because we have seen before that the model can take very long time to converge, right? The problem here is that this method is not compatible yet with the empirical classical option. So we cannot put the two in the same statement. But still, we can get accurate estimates of the fixed effects and also of the covariance parameter estimates. In the next method, we have like a two-step process. First, in the first model, we fit exactly the same model as we have seen in the previous method too, with the probability weight here and the fast QAP sub-option. Then we obtain, in this first model, the fixed effect estimate. And then we run a second model where we change slightly the second random statement. So basically, instead of using the probability weight, we use something called normalized weight. This normalized weight is calculated as dividing each respondent probability weight by its mean. So it's basically this formula here. And what we are doing with this is basically avoiding the overestimation of the sample size, which will avoid having too small standard errors. So once we have, for the first model, in the first model, the parameter estimates, the right parameter estimates, and once we correct it using the second model, the standard errors, then we can calculate the 95% confidence interval as is shown in this formula here at the bottom of the slide. Then the fourth method is what you have seen already. Like this is what we call the gold standard method, and it has all the features that are important for this type of model. Then finally, method 5 is also a two-step process. So in the first part, we also use the same method as method 2, where we have the fast QAP sub-option and the probability weight. And then, but the purpose of this first model is a little bit different from what we have seen before. In this case, we fit this first model with the goal of obtaining the covariance parameter estimates. So we fit this model, we obtain the covariance parameter estimates, and then we fit a second model, which is very like as the gold standard method, with the difference that we add the PARMS statement. As you see here, in this case, the PARMS statement has 4 covariance parameter estimates corresponding to the one that we previously calculated in model 1. So we fit model 1, obtain the covariance parameter estimates, and then we fit model 2 with a parent statement. The sub-option whole equals 1, 2, 3, or is telling us to is telling the model to constrain these 4 covariance parameters estimates to the numbers that I have provided. So now to test our method, or to illustrate our method, we use an example data. In this case, we are using the nationally representative cohort of 1,600, approximately 1,600 community dwelling seniors enrolling the Health and Retirement Study, or HRS. The HRS is an ongoing longitudinal survey of a representative sample of all persons in the United States over age 50, and it examines changes in health and in wealth. The survey features that are typical for the HRS are stratification, and we have in our study sample 52 strata. Clustering, we have 2 clusters. The differential selection probability, which I have been mentioning before as probability weight, and we derive this variable from prior interview. And then finally, we have a derived variable that you have seen in previous slide, and we call it cluster bar. And as I mentioned before, this variable is a combination of a strata and cluster, and it has 104 levels. Then the main predictors of this data would be a type of heart procedure, and we have 2 heart procedures that we analyze: the coronary artery bypass graft, we call CABG, or percutaneous coronary intervention, and we call it PCI. Our outcome is the composite memory score, and this is a continuous variable derived at interviews before and after the procedure. We followed the respondents 5 years before procedure and 10 years after the procedure. The total sample size was over 8,000 observations, corresponding to the over 1,600 respondents that we have in our sample size. And finally, our goal was to investigate whether there is a change in the cognitive slope following CABG or PCI, and whether this change in the slope was different depending on the procedure performed. Here we see in this table the results of the comparisons of all these 5 methods. Each column represents a method, and then in this column here we have the effects of fitting this mixed effects model. The first thing that I would like to highlight is that method 3 and 5 have very similar fixed effects estimates and also 95% confidence intervals compared with the gold standard method. And this was expected since both method 3 and 5, they incorporated probability weights, and also they adjust the standard errors of the model. In the case of method 3, we use the normalized weight, which I told you before, that is used to control for the overestimation of the sample size and getting 2 small standard errors. And method 5 used the sandwich estimator. So we expected that these 2 methods were very similar to the gold standard method. Then we have method 2 and 3 that have, if we look only at the fixed effects, they have very similar fixed effects compared to the gold standard method. And remember that this method both use the fast swap option. In addition, if we look at the covariance parameter estimates of method 2, 3, and 5, all of them have almost the same covariance parameter estimates as the gold standard method. So what this tells us is that using the fast swap option can be a valid alternative to obtain accurate fixed effects estimates and covariance parameter estimates. However, one needs to be cautious about making inferences on these fixed effects, because as we have seen with method 2, if we look at the effects, this one these two fixed effects, we see that the 95% confidence intervals are very narrow. And this is because we did not use the sandwich estimator. So this gave us very narrow standard errors, which can cause that we make wrong inferences about these three effects. So whenever we use the fast swap option, it's good to obtain the right estimates, but we need to be cautious about the inferences that we make on these estimates. Then between method 3 and 5, we found that method 5 actually have closer 95% confidence intervals to method 4, compared also with method 3. So we would prefer method 5 over method 3. And finally, we found that both method 3 and 5 reduce significantly the running time of the model. You can see that method 4 run for about 42 hours, and both methods have a reduced running time than what we had in the method 4. In the next slides, I'm summarizing what I just told you about, so we will skip through them. Then this figure, actually, we are now focusing on answering our research question. So remember that from last time, from previous slide, I mentioned that our goal was to see where there was a change in the cognitive trajectory before and after procedure between these two groups, CABASH and PCI. Well, we are focusing now on these fixed effects here, and this one tells us whether the pre-trajectory slope is different in these two methods. And what we can see here is that regardless of the method used, there is no significant difference in the slope prior to the procedure between CABASH and PCI. However, we can see that method 2 through 5 have more similar estimates compared to method 1, which did not use any probability weight. Also, it's interesting that method 1 has a different size of the FET, but also the sign of the FET is different. This one is positive and the rest is negative. So it would be up to the clinical researcher to determine where this difference in magnitude and also in direction is clinically relevant. Then we focus on seeing if this change in the slope from pre-trajectory to post-trajectory between these two procedures, CABASH and PCIs, is significant, has a significant difference or not. In this case, again, we don't find any significant difference among the different methods that we tried. And in this case also, the size of the FETs is very similar across methods. But method 2 through 5, where we did incorporate probability weights, are more similar among themselves compared to method 1. And this is the same that we found in the previous slide. One thing, though, that I want to point out here is that this method 2, the one where we only use the fast quotient option and we do not use any sandwich estimator or anything else, has too narrow confidence intervals. This is very important to highlight because this emphasizes what I mentioned before, that when we're using just fast quotient option, we need to be careful on the interpretation of the inference of this effect that we obtain, because this one we might think that it has very narrow confidence interval when in fact that's not the case. As a conclusion, we have seen that fitting a mixed effects model that accounts for solvay feature is very important to obtain accurate and precise estimates. However, when we have a mixed effects model with many levels of strata and cluster, this type of model can be very computationally intensive and complicated to optimize, which in turn have the model will have long running times. We have seen in this presentation that the fast quotient options, the parent statement, and the use of normalized weight can be used to produce reliable estimates while at the same time reducing the running time. My colleague Bochen Jin, who is the second author of this paper, and I I would like to send for the support the UCSF Pepper Center Development Award and the National Institute on Aging. And with this, I conclude my presentation, and I thank you all for your attention.